All right, number 6 was a work problem, pumping liquid out of this hemispherical tank up to a level 5 feet above the top of the tank. This one caused some trouble. People didn't read closely enough that said hemisphere. So I got some other shapes here. The hemisphere is key, right? We can think of this as a volume of revolution of a circle. So the equation of a circle, again, is coming into play. And interestingly, people who did not get the equation of the circle in question 1, they didn't necessarily not get it here. So not sure what happened there. But first of all, in these application problems, I can't stress enough, draw a coordinate system. Still saw a lot of problems with no picture, no coordinate system. I'm not sure how you're determining what the integral is without a sense of where you're at, what the values are. So start with a picture. You have time. Take the time to sketch the picture. You're much less likely to make a mistake. I think a good picture will lead to a good setup, and you'll be good. So the thing to understand is that a hemisphere is a volume of revolution. So when you're taking your slice at C sub k here, what do? This is really a step back. Even though this is applications, it's a step back to volumes of revolution, right? Because we're interested in the volume of this liquid, a slice of this liquid. Well, how do we approximate a volume? Cross-sectional slices. So there's our cross-sectional slice at C sub k. And as long as I can describe what's happening to that one slice, then I can write my integral. So first of all, in the geometry of this slice, it's the geometry of a right circular cylinder, right? That's what cross-sectional slices are. The height here is simply the change in y, right? So that's my delta y sub k. And then I'm going to need the radius, because the volume of this thing is pi r squared, the area of the base, times the height. I know height. I just got to figure out r. Well, the radius of this circle is being determined by the curve, right? The distance from the axis of revolution out to here is simply the x-coordinate, right? Well, how do I relate x to my y value, C sub k there? That's where the equation of the circle comes in, right? I need to describe this curve algebraically. And so it's centered at the origin. Now remember, you could put this coordinate system anywhere you like. You could have that sphere shifted up or down. Your answer will be equivalent. But centering a circle at the origin makes its equation the nicest. So that's what I do. This is x squared plus y squared equals r squared, or 81. This is a radius 9. OK, so down here, I need x squared. Well, x squared is 81 minus y squared. And my y value is c sub k. So r squared is x squared, which is 81 minus c sub k squared. And my height is delta y sub k. One of the things I saw a lot of, and I see this a lot actually, is people want this to be formulaic. And I think they get in their head that I need a volume. So what I see is pi r squared. OK, I've got a sphere. The radius is 9, so r is 9. We don't care about the whole hemisphere. We care about one slice, because then we're going to integrate all the slices. So although this radius is important in determining this equation, it is not the radius of every slice, right? This one, if I slice here, 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 they all have different radii. So it's not a fixed radius situation. The only thing that would have fixed radius would be a cylinder, right? If this tank was a cylinder, then no matter where I sliced it, they would all be the same size. But the radius is changing on that. So don't make that mistake. this is typically going to be a function of y, or c sub k in the slice here. Okay, and the other thing you had to determine was how far. So think about what the work is on that slice. So work, remember, is force times distance, and the force involved here is gravity, right? We're adding gravitational potential by lifting that water up to a higher height. So what we want is the weight of that water, which is its volume times its weight density times its depth. So we've figured out volume, or at least our approximation, right? It's definitely the volume of our approximation. There's volume. And if I'm not mistaken, we just had the standard 62.4 pounds per cubic foot on the weight density. And then D is how far are we lifting it up? So if we come over here, it's starting at c sub k, right? And it's ending at 5. So that distance is 5 minus c sub k. So there's our last piece. And then, so when we set up our integral for work, remember when you're thinking about what are my limits of integration, you know, some people get confused. Do I go from -9 all the way up to 5? Well, ask yourself, what are you slicing? I'm slicing the water, so my partitioning is from -9 up to 0. The 5 is important. It comes into play here, but it's not where we're integrating. We're integrating up the slices there. Okay, and then all of this, 62, kind of rearrange things into a nicer order, but make sure I get everything in there. And there's our integral. And then the other thing I wanted you to give me was, what would the units be? Well, think about it. Work is a force times the distance. Distance were given in feet. The forces were given in pounds, so we know from the setup that it's foot-pounds. Some of you wrote pound-foot, which I put a note on there that it's standard for us to, we actually sort of standardly say foot-pounds, although it is, you could argue that it's multiplication, so either way is fine. I did put a note. You didn't lose points if you said pound-feet, but that is the standard way of saying those units is as a foot-pound, not a pound-foot. So yeah, draw a picture. Label the coordinate system. Make sure you read the problem. It's a hemisphere. And I think if you have this detailed a picture, I can almost guarantee this integral is going to be set up right. It's hard to have all of that information laid out in a picture and not arrive at this. And just for a practical concern, if there's no coordinate system there and I look at your integral and it doesn't look like what I'm expecting, I don't know if it's right. Maybe it is, but be careful. You know, I can't sort of read your mind of what you meant to do there. And if something is wrong in there, then I don't know which coordinate system to give you credit for. So be careful of that. Oh yes, one more thing. This came up for several people, and this is common. A lot of people would like to avoid negative numbers, so they put the coordinate system with the bottom of this hemisphere at 0. That's totally fine. You would integrate from, this now is 9 up here. So you'd integrate from 0 to 9. But the thing to be careful of is this is no longer the equation, right? The center here is now up at 9, or what, 0, 9. So the equation of that circle that's being revolved to create the hemisphere would look like that. It's got a shift in the y direction. So it doesn't matter which coordinate system, one's not right or wrong, but that's the equation for that thing. That's the equation for that one. So be careful of that. If you want to use that setup, make sure you got the equation right. And I think that was it. Just make sure clean picture will lead to a nice integral. And if you're shifting, just be careful you've got the right equation there. In all my talking, I wasn't paying close enough attention to what I was writing. It just pointed out to me that I wrote that down wrong, right? The equation of a circle is x minus h squared plus y minus k squared equals r squared. That is not ever a minus there. Actually, if that's a minus, we're getting into a hyperbola. That is not a hyperbola. We want this to be a circle. So yes, that should be a plus there. Sorry about that.